Here we have a problem involving 3 equivalent light bulbs in a circuit, and we're asked to think about the brightness of the different bulbs compared to each other and to rank them. And at first it says to justify your answer qualitatively, and I'm going to do just that, and then I'll try putting some numbers in so you can see it quantitatively as well. So question A is to rank the brightness of the identical bulbs in the circuit above, which is the brightest, and are any equal to each other, what is it? And if I were to do that right now, I would conclude that we're going to have bulb A as the brightest, and that's going to be brighter than bulb B, and C will be equal to each other. All right, so bulbs B and C are the same. Bulb A is the brightest. Why? Quantitatively? Well, if you just look at the way the circuit is, okay, you realize immediately that the voltage drop across bulb A, so that's the voltage that would be read by a voltmeter that I put here, is equal to the voltage drop across both bulbs B and C. These 2 voltage drops are equivalent to each other. Now they're not equal to the voltage of the battery itself because we've got this sort of this extra resistor right here. Okay, but whatever the voltage drop is across bulb A, it has to be the same as across the combination of bulbs, bulb B and C. So since the bulbs are identical, that means that each one of these bulbs has a voltage drop of half of this entire one. So this, we would write this as, this would simply be called V over 2. Right? And similarly for the other one. Now we know that power, the formula for power, is current times voltage. Right? And so the brightness of a bulb is a direct measurement of its power output. So bulbs with higher power outputs are brighter, obviously. Well, bulb B already has half of the voltage that bulb A has. So it's dimmer than bulb A. Similarly, bulb C has half of the voltage that bulb A has across it. And so, again, it is dimmer than bulb A. But it's even worse than that. It's inappropriate, or it's not inappropriate, it's incorrect to suggest that the power output of bulb B is precisely half of the power output of bulb A. In fact, it's worse than that. The power output of B is actually a quarter of the output of A, and the output of C is actually a quarter of the output of A. And to see why, you have to think about the other term in this power formula, and that's the current. So if you think about how that's going to work, this branch of the circuit, which has only a single bulb in it, will actually have twice the current as compared to this branch. So if I call this current I, then I'm going to have to call this current 2I. And it should be apparent why that is, right? I've got twice the resistance with bulb B and bulb C that I have up here with bulb A. So I get more current flowing through bulb A. So that means that bulb A has both more voltage across it than bulb B and more current through it, and both differ by a factor of 2. When you compound, when you put those 2 effects together through multiplication, in this case, you wind up with a scenario where you find out that bulb A has 4 times as much power as either bulb B or bulb C. Okay, I hope that's clear. Now we can do that with numbers if you want to, and to make it work out nice, if you want some nice easy numbers. A good set to use would be 12 volts for the battery, and then call each of the light bulbs 3 ohms. Okay, so they're all 3. And then this resistance over here, make it 2. All right, and if you do that, it just works out rather nicely. The way you can combine the numbers, I just picked them so that they work out simply. What you do get if you work that all out is you wind up with a single equivalent circuit that has an equivalent resistance of 4 ohms. right? And then I've still got my 12-volt battery. That makes, all nice, easy whole numbers. You can just kind of work it out. And when you do that, it's a simple matter to calculate the current, and then you get the power in every light bulb, and you can actually numerically compare those power values to each other. And what you'll see is that indeed the power output of bulb A is 4 times the output of either C or B. Okay, I'm not going to bother to do that right now. I'll just leave that for you to do if you want. But you probably should, to make sure that you know how to reduce these somewhat simple circuits to even simpler circuits. All right, moving along to B. If resistor R is replaced with one that has half the resistance, what does that do to the ranking? Does it change your ranking of the bulbs? Well, certainly if I replace resistor R with a smaller resistor, then there's less voltage loss across this particular resistance, and the current in the circuit also increases, right? Because with less total resistance in the circuit, the current does increase. But that doesn't change the relationship between the bulbs, right? It's still going to be true that there will always be twice as much current in bulb A as there is in either bulb B or bulb C. And there's still going to be twice the voltage drop for bulb A compared to either bulb B or bulb C. So I don't think the relationship changes, right? It's just, would maybe all the bulbs get brighter if I decrease this resistance R over here? Fine, but that doesn't change how you rank them. But the last question is, well, what would happen if I actually shorted out the resistor? Right? What would happen if I just kind of came and took and put a wire just like that right around that resistor, and it's assumed that that wire has no resistance inside of it? So now I've given electrons a free pass around that resistance, and immediately would reduce the current in that resistor to 0, and the voltage drop across that resistor to 0 as well, so that now all current follows the red line. What does that do to the brightness of B compared to what it was before? So now I'm not comparing bulbs to each other anymore. I'm just comparing bulb B now to bulb B before I put the wire. So kind of a switch in what we're doing. And it's really easy to get messed up in understanding that when you're reading through the question quickly. So obviously if I short out resistor R, then I've lowered the overall resistance in the circuit, right? Because I've removed, effectively, I'm not requiring any current to go through that resistor anymore. There's a free pass around it, a toll-free lane to go around the toll booth, or whatever you want to call it, right? A free exit from the grocery store without having to wait in line and pay for your groceries. Everybody's taking it, and everybody's going to go that way. And so if I do that, then the overall resistance in the circuit goes down, and that means the current goes up. So of course I expect to see all the bulbs get brighter than they were before. And in fact, B is one of those bulbs, so B gets brighter. And that's it.